You know, every single thing around us, at every moment, is being pushed and pulled by invisible forces. It's like a constant, silent tug of war. So how in the world do we make sense of it all and predict who's going to win? Well, that's exactly what we're about to figure out. It really can feel like total chaos, can it? You've got all these different forces, all acting at once, pointing in different directions, with different strengths. I mean, how could you possibly know if something is going to move or speed up, or maybe just stay exactly where it is? That's the big question, and we're going to get you the answer. And here's our game plan. We're going to start by meeting the main forces at play. Then, I'll introduce you to an incredibly powerful yet simple tool that organizes it all, the free body diagram. We'll use it to solve a couple of problems, and by the end of this, I promise, you'll have a brand new way of seeing the world around you. All right, first things first. Before we can understand the story, we've got to meet the cast of characters. Getting a handle on these common forces is really the foundation for predicting, well, pretty much anything that moves. First up, we've got tension. Just picture a classic game of tug of war. That feeling of the rope pulling on your hands? Yeah, that's tension. It's a textbook contact force, meaning the rope has to actually be touching you for you to feel its pull. And then, of course, there's the big one, gravity. It's that fundamental pull between any two objects that have mass, like the Earth pulling you down into your chair right now. But here's the really mind-bending part. It's a non-contact force. The Earth doesn't have to touch an apple to make it fall from a tree. It just reaches out and pulls. Okay, so if gravity is always pulling your chair down, why doesn't it just sink right through the floor? Well, say hello to the normal force. It's the floor pushing back up. The word normal here is just a fancy way of saying perpendicular, or at a right angle to the surface. It's a perfect real-world example of Newton's third law. For every action, there's an equal and opposite reaction. And last but not least, there's friction. You know it well. If you try to slide that heavy chair across the floor, you feel that resistance fighting you? That's friction. Its whole job is to oppose motion when two surfaces try to slide past each other. So we've met the players. Tension, gravity, normal force, friction. But what happens when they all decide to show up to the party at the same time? It gets complicated fast. Well, physicists have this brilliantly simple tool for cutting through the noise. It's called a free body diagram, and it's our blueprint for bringing order to all this chaos. And you're not going to believe how easy it is to make one. Step 1, you take your object, a car, a person, whatever, and you just represent it as a single dot. Seriously, a dot. Step 2, you draw arrows pointing away from the dot for every single force acting on it. We call these arrows vectors because they show us two things at once, the direction of the force and its strength. Which brings us to step 3, make the arrows for stronger forces longer and the arrows for weaker forces shorter. That's it. That's the whole thing.
All right, enough talk. Let's actually put this thing to work. We're going to take what looks like a messy problem and see how this little diagram makes the solution feel almost obvious.
Okay, so picture this. We've got a box sitting on the floor. There's a spring pulling it to the left with 200 newtons of force. At the same time, a rope is pulling it right with 160 newtons. And of course, gravity is pulling down with 80 newtons, while the floor pushes up with 80 newtons. So, where's it going to go? Now, here's the secret sauce. The trick is to stop looking at it as one big jumbled mess. Instead, we split it into two super simple problems, one for the vertical forces and one for the horizontal forces. We'll call the up and down the y-axis, where up is positive, and we'll call the left and right the x-axis, where right is positive. Now all we have to do is some basic addition for each one. Let's start with the vertical axis. The floor pushes up with 80 newtons, so we'll call that a positive 80. Gravity pulls down with 80 newtons, so that's a negative 80. You add them together, and you get a big fat 0. So what does that tell us? It means the vertical forces are perfectly balanced. The box isn't going to suddenly fly up to the ceiling or sink into the floor. Vertically, it's locked in. Okay, now for the real action, the horizontal tug of war. The rope pulls to the right with 160 newtons, so that's positive 160. But the spring is pulling left with a stronger 200 newtons, so that's negative 200. The result? Negative 40 newtons. And that negative sign isn't just a number, it's a direction. Since we decided left was negative, we now know for sure that the overall, or net force, is 40 newtons to the left. The stronger spring wins. See? Simple.
So that was pretty clean, right? But you might be thinking, sure, that works for a simple box, but what about more complex real-world stuff? Well, let's test it. Let's up the difficulty and take a look at a hot air balloon.
So imagine this balloon is rising, but the wind is also pushing it so it drifts to the left. It's got gravity pulling it down, but the buoyant force of the hot air is pushing it up. And because it's moving, it's also got air resistance, or drag, fighting its motion both vertically and horizontally. Whoa, that's a lot going on. But here's the beautiful part. No matter how complicated this looks, the process we use is exactly the same. We just have to trust the method, separate the vertical forces from the horizontal ones, and the whole picture becomes crystal clear. Let's knock out the easy one first, the horizontal axis. So the problem says the wind is making the balloon drift to the left, which means the drag force from the air is pushing it back to the right. And that's it. It's the only horizontal force in the whole problem. So the net horizontal force is simply that drag force, a positive 5,000 newtons. Done. Now for the vertical. We have this really powerful buoyant force pushing up with 10,000 newtons. But there are two forces fighting against it, pulling down. 4,000 newtons from gravity and another 2,500 from drag. So we take our upward force and subtract the two downward forces, and we're left with a positive 3,500 newtons. Since up is positive, we know the balloon has a net upward force and is going to keep on rising. And just like that, we've brought perfect order to a really complex system. You see, this isn't just a trick to pass a physics exam. What you've just learned is a fundamentally new way to see the world. It's like gaining a superpower that lets you visualize the invisible web of pushes and pulls that governs everything.
So let's just quickly recap the big ideas. First, forces are vectors. They've got both a strength and a direction. Second, a free body diagram is our map to visualize all those forces at once. Third, and this is the magic key, you always split the problem into horizontal and vertical parts. And finally, when you do that, this incredibly simple tool can bring order to even the most complex systems you can imagine.
So I want to leave you with this thought. The next time you see a car going around a corner, or a bird gliding on the wind, or even just a simple picture frame hanging on your wall, just pause for a second. Now that you can map these unseen forces, what do you see? And how does that change your perspective? Thanks for joining me.